Oh, I didn't see you there. Welcome back. We are doing the pair t-test. Early morning hustle. You can do it, and we're doing the pair t-test today. So go ahead, read the description. You know the deal. Look at the summary statistics, the visualization, as well as the analysis, and we'll come right back. Well, welcome back. An organic farm in Willamette Valley evaluated their new natural pest control method by examining pest damage in 45 tomato plots. They counted damaged tomatoes in each plot before implementing the control method and again at the same locations after 30 days. By calculating the difference between before and after counts for each plot after minus before, they found a mean difference x bar d negative 4.2451 damages per plot with a standard deviation of 3.8685, indicating the change in pest damage across the observational period. So in this particular description, it's important to note that we are looking at the same plots being measured before and after. And the reason why we're doing that is so that we can actually determine if the conditions, like the condition of one particular plot, might be more varied or may have less damaged tomatoes. So we want to make sure that we're looking at the same plot so that we can account for plot-to-plot variability, okay? To account for plot-to-plot variability. So we are associating these two groups. These two groups are dependent upon one another because we're measuring them twice so that we can see plot-to-plot variability, okay? And so in terms of our visualization, each point, okay, I would say this is a dot plot, okay? Each point, right, denotes a plot, okay, of where tomatoes are being grown, okay? And then each point has a connection to the before point in terms of the number of damaged tomatoes. So this is the number of damaged tomatoes after pest control, and this is the number of damaged tomatoes before pest control. So as you can see, and then this red line, red bordered line, this is connected to the mean of after to the mean of before. As you can see that there is a dip, it's decreasing. But is it by chance? Is it statistically significant in terms of this difference? We'll go ahead and look at the analysis to find out. So this is my test statistic. That's a huge test statistic. This is my degrees of freedom, and this is my corresponding p-value. Okay. This is my confidence interval, and this is my mean of the differences again. As you notice, 0 is not within the lower bound and upper bound, right? And what does 0 mean? 0 means that there's no difference. Okay. So based on our data, we can say that 0 is now within. There is a difference between after and before. That's a confidence interval. With confidence interval, yes. And so therefore, not therefore, but in following or furthermore, you can actually see this kind of conclusion in terms of our hypothesis test. This is our test statistic. This is the corresponding p-value. Okay, so based on our p-value, if you were to think about the connection between hypothesis testing, we should reject the null hypothesis, indicating that the mean of the differences is equal to 0. Okay, so with that being said, let's actually continue on to the questions. So take a moment, answer questions 1 through 7 like we've done in the past, and then answer question 8. We'll answer those together, and then we'll answer question 8. All right, so why does this research matter in real world? In real world terms, is because you can imagine being a farmer, you would want to make sure that the pest control actually has an impact on decreasing the amount of damaged tomatoes. So that's our rationale, okay? In terms of variables, it's not 2. And I understand why people think that it's 2, but it's really just 1. What is the main variable that we're analyzing in this situation? We have the before number of damaged tomatoes and after the number of damaged tomatoes. And what we're really after in terms of that particular plot is the difference. And that difference is a quantitative variable. Okay, so we only have one variable in the situation, which is just the difference in the number of damaged tomatoes. Okay, And I'm trying, in this next bullet point, or at least this next point that I'm trying to make here, is that I kind of emphasized this earlier, is that the variable, okay, the number of damaged tomatoes before and after makes each of the plots associated with one another. So, or each group before and after has a point that's seen in both groups. So that's the pairing that we are observing. The observation unit is going to be a plot. Okay, each tomato plot. And why do you suppose we decided the same observation twice? Because we want to account for plot-to-plot variability. Some plots may perform better in terms of damaged tomatoes, and some plots may perform worse, and we want to account for those differences by measuring both of those plots within both of those treatments. What's really important in terms of really implementing this in real life is that we apply the 30-day waiting period so that we can actually see the impacts of the pest control. Okay. So we measured the same plots twice before and after treatment, since the paired design allows us to directly track changes in pest damage while controlling. That's us controlling for plot specific characteristics. So some plots may have better soil quality or have better sunlight exposure and so on and so forth. Okay? And so hopefully that I'm trying to beat that point to understanding. So rewind if need be or ask me questions. I'll be more than willing to answer them. Who or what makes up the population, the target population? And that's going to be all the plots on the farm. How did we collect the sample? In some way, shape, randomly. 45 plots were randomly selected, okay, to represent the actual farm's plots. This was definitely an experiment, right? Because we're manipulating. We're actually providing some treatment, okay, to the plots. And then the statistical technique is a paired t-test. And we didn't explicitly say that it's a hypothesis test, but we are going to do a hypothesis test. Okay. All right. So take a moment and answer question 8 in terms of these following characteristics. Okay. Nothing new. Nothing new. All right. So this time I'm actually going to explicitly state the parameter of interest and its sample statistic here. Okay. So, and also in terms of context. So in terms of the parameter of interest and the actual statistic of interest, that's going to be the population mean of the differences. The population mean of the difference in the number of tomatoes, number of damaged tomatoes, sorry. And that's mu D. And we're going to estimate that with X bar D, which we can actually calculate. Okay, negative 4.245 is the sample mean of the difference in the number of damaged tomatoes. Okay? And since it's negative, that's also telling you the sign, right? That they're doing after minus before in terms of visualization. So you can use the actual visualization to tell you that they're doing after minus before. Okay? And the test statistic is also negative, telling you that as well, which we'll see in a moment. All right, so then from there, in terms of symbols, this is our null hypothesis. The population mean of the differences, as you can see the new symbol, mu D, is equal to 0. Whereas the alternative is that mu D is what? Not equal to 0. Okay, the population mean of the differences of the damaged tomato due to pest control method is not equal to 0. Not 0. Okay? So notice that we're using those the parameter mu D. From there, in terms of assumptions, there's 2. As you already know, randomness needs to be involved in some way, shape, or form. But there also needs to be some type of an association between the groups. Okay, there needs to be some pairing. Since we're doing a paired t-test, there needs to be a paired association between the groups. Okay, so those are the 2 assumptions. And then finally, well, in terms of our test statistic, it kind of reminds us of one sample mean test. Okay, but instead this should be X bar D. x bar d. Okay, so it's the sample mean of the differences minus mu d, the differences, which is our hypothesized value, which is really 0, right? That's just a 0, divided by SD over the square root of n is equal to negative 7.613. Okay, that is our test statistic. Our degrees of freedom is going to be n minus 1, which gives us 45 minus 1, which gives us 44. And then finally, our p-value is extremely small. So I didn't emphasize this in the last video, but again, emphasize this in the other video, is that we have a symmetric distribution that's unimodal. If it's beyond 3.5 or negative 3.5, we know that the p-value is extremely small. And so we're not surprised that we have this here. So we have extremely strong evidence to do what? Reject the null hypothesis. Okay, reject the null hypothesis. So what this means in terms of like the context is that our pest control works. This new pest control mechanism definitely works. So let's use it again on more plots, right? And so based on the pair t-test, we have a p-value of 3.3 times 10 to the negative 9, we decided to reject the null hypothesis. We have extreme evidence against the null hypothesis, okay? The farm should consider implementing the method more broadly, ensuring continuous monitoring and cost-benefit analysis to assess its sustainability and effectiveness across different conditions, okay? So this actual method, at least our analysis tells us that the pest control did have an impact, okay? Good job. Thank you for watching and have a great day.